Okay, let's talk about function transformations. They're a huge part of math, but man, they had this nasty habit of tripping us all up. So today, we are going to crack the code on a method that'll help you get them right every single time. All right, be honest with me for a second. Has this ever happened to you? You've done all the hard work, you totally get the concept, but your final graph is shifted left when it should be right, all because of one tiny sign. It is so frustrating, right? And trust me, you are not alone in this. It's so common that even the textbooks admit it. I mean, listen to this from one pre-calculus guide. When performing multiple transformations, it is very easy to make a small error. Well, those small, annoying errors are exactly what we're going to eliminate today by thinking about this a little differently. So why does this keep happening? Well, I like to call it the transformation trap. And it's that moment where your brain just hits overload, trying to keep track of way too many steps at the same time. I mean, just think about it for a second. You're trying to visualize a reflection over the x-axis, a horizontal stretch, and a vertical shift, all at once. It's like juggling. And one wrong move, and everything just comes crashing down. That mental overload, that's the real reason we make those simple mistakes. So, okay, how do we escape this trap? Well, it all comes down to understanding that there are basically two different languages to describe the exact same transformation. They both get you to the same place, but one of them gives you a much clearer map. First up, we've got function notation. This is probably the one you've seen the most. It's the classic algebraic way of writing the rule, where you're describing what's happening to the function as a whole. Something like g of x equals f of x minus 3. And then here's the second language, point notation. Now this is different. Instead of a big rule for the entire function, this is a direct command for each and every coordinate point. It tells you exactly what to do to your x values and your y values. Honestly, think of it like a set of instructions. Okay, let's put these two languages side by side with a really simple example. Let's say we want to move a function right 3 units and up 4. So, in function notation, the language of the rule, that's written as g of x equals f of x minus 3 plus 4. But in point notation, our map, it's a direct command. X comma y turns into x plus 3 comma y plus 4. See the difference there? The plus 4 for the vertical shift, that's easy. It's intuitive in both. But look at the horizontal shift. It's x minus 3 in one language and x plus 3 in the other. That right there, that's the source of all the confusion. All right, so let's solve this mystery once and for all. Why on earth does the x-coordinate seem to work backwards in function notation? I'm telling you, this is the single most confusing part of this entire topic for almost everyone. Okay, first, let's get the easy part out of the way. The y-coordinate, it's totally intuitive. It does what it looks like it should do. Anything happening outside of the function's parentheses affects y directly. So a plus 4 on the outside means, you guessed it, you add 4 to your y value. Simple. Logical. No problem there. But now for the big question. Our brains see x minus 3 and just scream move left, right? But we're always told it means move right. So why is our intuition so wrong here? Okay, here's the secret. Function notation isn't giving you directions. It's telling you what you need to do to the input. So for f of x minus 3, the function is kind of asking, hey, what new x value do I need to plug in to get the same result I used to get from the original x? And to counteract that negative 3 inside the parentheses, your new x value has to be 3 units larger. So you see, it's describing the destination, not the journey you take to get there. And here's a key insight right from our source material. The new x-coordinate, it comes from undoing the operations that affect x. That's the key word, undoing. So when you see x minus 1 inside the function, the actual action, the actual command for your coordinate point is the opposite. You have to add 1. That's the shift. Okay, so now that we get the why behind the madness, let's put our new favorite tool, point notation, into action with a trickier example. Because this is where it really, really shines. All right, take a look at this beast of a function. G of x equals negative 2 f of x minus 1 plus 4. Wow, we've got a reflection, we've got a vertical stretch, and we've got shifts in both directions. Trying to visualize all of that at once? That is the exact trap we were talking about earlier. So instead of doing that, let's just translate it into our friendly language, point notation. Here's how we build our map step by step. It's super simple. First, let's look at the horizontal part. Inside the function, we see x minus 1. To find the action, we just undo it, right? So our x-coordinate becomes x plus 1. Easy.
Next, the vertical. We just look outside the function. Our y is first multiplied by -2, and then we add 4. We apply those operations in that exact order directly. So y becomes -2y plus 4. And now we just combine them into one single, super powerful map. X comma y becomes x plus 1, -2y plus 4.
So to really see this work its magic, let's just grab 3 key points from whatever our original function was. Let's say we have the points -2, 4, 0, 0, and 2, 4. These are our starting points, our before picture.
And here, this is where it all just clicks into place. We take our map, our rule x plus 1, -2y plus 4, and we just apply it to each point one by one. So let's do the first one, -2, 4. The new x is just -2 plus 1, which is -1. The new y is -2 times 4, which is -8, and then plus 4, which is -4. So our new point is -1, -4. See that? There was no guessing, no mental juggling. It was just simple arithmetic. It's totally methodical and pretty much error-proof.
So what you've just learned here, it's really more than just a cool trick. It's a whole systematic approach. It's basically a new secret weapon in your math toolkit for tackling these kinds of problems with way more confidence. The most important thing to remember is that point notation takes all that confusing mental gymnastics and turns it into a clear step-by-step process. It lets you stop worrying about the whole graph at once and just focus on one simple calculation at a time. So let's just do a quick recap of why this is so powerful. First, it makes those confusing horizontal shifts totally intuitive. Second, by turning it into a clear procedure, it helps you avoid all those little sign errors that drive us crazy. It also lets you concentrate your effort on one point at a time. And hey, even if you're great at visualizing, this is an absolutely fantastic way to double-check your work. Ultimately, what we're doing is translating the function's rule into a coordinate points map. And by doing that, you've created a super clear path directly to the right answer, every time. So really, the only question left is, now that you have the map, where are you going to take it?